Hi everybody, welcome back. How's it going? So last time we looked at the idea over here, which was the gradient vector. Okay, so we just said it's just a linear algebra way of saying get the derivatives of the MSE with respect to each of the beta components, and then you set that all equal to 0. And that's the same thing we did with simple linear regression. And so what it does is you can solve that to get some formula that I haven't showed you yet. And so I'm going to throw this equation at you, and I'm going to explain just a little bit about it. I'm not going to do the same kind of explanation that I did over here because this explanation actually really makes sense and it's not super complicated. Over here, let me show you a couple things. So first, if I was to let y as a vector equal just our real predictions, okay? So it was, sorry, not predictions, our actual observed values, okay? So y1, this is going to be the observed value that we were trying to predict for, but the actual value for the first person. And so this all the way down is just, this last thing is for the nth person, our observed real actual value. Okay, so it turns out that the formula for beta hat, which means this is a vector, okay, so our vector of betas, but the betas that minimize the MSE, which I'll write explicitly as beta naught hat, beta 1 hat, all the way down until beta p minus 1 hat. Remember p things, so p minus 1 there. And so each of these things are the right value that minimize the MSE. And we can get this whole thing in one go as x transpose x, and I just did the transpose of a matrix, which I haven't even showed you yet, x transpose x inverse, which I have not explained the inverse of a matrix yet. This thing is a matrix, and the inverse of that is a matrix. So x transpose x inverse x transpose, I haven't showed you the transpose of a matrix still, y. Okay, so hopefully that made no sense. If that did make sense, then good job. The point is that this is a bunch of different components, and I'm not going to explain the whole thing, but I want to give different intuition into what these are, just so that the linear algebra makes a little bit of sense. And if you wanted to derive it yourself, not deriving the actual answer is very difficult. You could look it up, but at least showing this component is not too crazy. But x transpose, if x was, say, and I'm going to write this instead of thinking about it as row vectors, it's really just a bunch of components. What I'm going to write right now as x11, x12, and I'm just going to show you this on an example of a matrix and not worry about the dimensions of like an arbitrary matrix. So this is x11, x12, and we'll say x13. So the first subscript is which row, and the second subscript is which column. So then this would be x21, x22, and x23. All right? If I was to take the transpose of a matrix, x transpose is equal to, it turns out, and I'll put it over here for room, it looks like this, where, remember I said before, it turns, for a vector, it turns a column into a row, or a row into a column. And so it does a kind of similar thing here. It changes the shape of it so that its rows are columns, and you could also think about it as its columns or rows. So this first thing, as a row, this goes down like this. So this would be x11, x12, x13. Okay, so it changed the shape like that. And this thing over here, this is a row, it turns it into a column. So this goes over like this, x21, x22, x23. All right, and that is the transpose of this matrix. That's all it does. And so you could think about that in the same type of way as instead of changing rows to columns, this is two rows, so it changed these two rows into two columns. Well, you could think about it as these are columns instead. So if I was to show instead what I was writing, I got rid of these, sorry about that. If I got rid of these circular things here, and I showed you instead that you thought about it as a column or a bunch of columns, well, then you'd have, this is a column. Sorry about that again. This is a column, this is a column, and this is a column. And so this column turns into a row, and this column turns into a row. This column turns into a row. So it's basically the analogous thing from a vector transpose, the analogous thing for a matrix. And the inverse, well, I'm just going to write down that basically it means, and there's a lot more to this, and I might be a little bit sloppy with the math here, it's just intuition, is that if we had another matrix, so this is X, and then we had another matrix called X inverse, the inverse of X, well, that would equal I. And in linear algebra, I is this matrix, where it looked basically like this, where the ones are on a diagonal and everything else is 0. Okay? And I wasn't worrying about the particular dimension of this thing. This dimension might have been wrong. It might not have looked just like this 3x3 thing. I'm just saying for whatever X is, you can look up exactly what the inverse of it is. But really it's the matrix that when you matrix multiply it, which again, I hope you didn't understand because I haven't even defined matrix multiplication, and I'm not going to right now. It's the matrix that makes up this thing. And so that's kind of like a scalar. So if you were to have some value, like say 5, well, 5 inverse, or 1 over, is equal to, this is 5 times 1 over 5, which is equal to 1. Okay, so it's kind of analogous to that, to matrices, and there's a lot going on there. So if you didn't understand this one, really not a big deal. It was just some insights into some of the linear algebra that we were doing. And the point is that we have some formula here. Okay, so we have X transpose X inverse X transpose Y, and we can do that in what we'll see as NumPy, so that we're able to do this in Python. So that is all that we need, linear algebra and calculus, to actually implement this in Python. But we need to look at NumPy first, because NumPy is the base stuff for linear algebra type work. So I'll see you in the next video when we hop on the Python stuff.